Well, hello, and welcome to our next video on parametric equations and how they're applied in calculus. In this video, we're going to take a look at the idea of arc length. How do we find the length of a curve if it is described using parametric equations? This is a very important application because parametric equations often are used to describe motion in the plane or space. So as the parameter t changes in your parametric equations, the equations give the position of an object at time t, and the arc length then tells you the distance the object has traveled and is also closely related to the speed and velocity of the object. So suppose we have a curve described by parametric equations. X is a function of t, y equals y of t, another function of t. We'll say t is restricted to be between a and b. And if these functions are differentiable and the derivatives are continuous, we can come up with a method for calculating the length of the curve C. And we're going to do this in a manner similar to the way we found the length for a curve C described by Cartesian equations. That was done earlier in our course. As we did for Cartesian described curves, we're going to partition the curve into small pieces, estimate the length of each piece, sum these lengths to get a Riemann sum, and then take the limit as the norm of our partition goes to 0, and through this we'll arrive at a definite integral whose value is the length we seek. So let's suppose we have a curve C, again described by these parametric equations C listed here. We'll start by partitioning the t interval. So t between a and b, and our partition, again, is as always just a set of points in the interval, and they are listed here. And as always, we assume the values are increasing with index. The left point, the first partition point is t0, which is A, and then t1 next, then t2, etc. And the last partition point turns out to be B. And you see them laid out here on this axis. As usual, let delta t equal tk minus 1. So delta t, k, then denotes the length of the small kth interval. Here you see delta t1 going from t0 to t1, and delta t2 going from t1 to t0, etc. Now, each of those values, those t values, t0, t1, t2, etc., when we run them through the parametric equations, x equals xt, y equals y of t, they give us a point on the curve C. And so for k between 0 and n, we're going to let pk denote the pair x of tk, y of tk. Again, that's just a point on C. And so, in effect, the partition of the t interval is going to lead to a partition of the curve. We can see what that looks like in the next picture. So here's a picture of some of the points p sub k on the curve. So here's p sub 0, and that is just the result of applying x to t0 or a and the y function to t0. Again, a, and so p0 is that point, and this notation continues around the curve, and here we've actually written out the p sub k minus 1 pk. As usual, at delta sk, k running from 1 to n again, be the length of the piece of the curve C between pk minus 1 and pk. So we've included the delta sk's in the picture we see here. And so from p0 to p1, we're going to say this curve C has exactly length delta s1. Here's length delta s2, etc. And our kind of generic example from pk-1 to pk, length delta sk. Now, we're then going to approximate delta sk by drawing the straight line segment joining pk minus 1 and pk and finding the length of that straight line segment. So in this picture, we've now just drawn these red segments. So we're kind of approximating the graph by a bunch of straight lines. We're going to find the length of each of those red segments just using the distance formula. Recall if we have a segment in the plane and we know the two endpoints of the segment, for example, here are the endpoints of the kth segment, then the length of that kth segment is just found by doing the difference in the x-coordinates, x of tk minus x of t sub k minus 1, all squared, and then adding to that the square of the difference of the y-coordinates. And so this is going to give us an approximation to delta sk. The curve itself might not be a straight line, so the straight line probably won't give the exact length delta sk, but if our partition is fine enough, it should be pretty close. So we first do a little algebra to simplify this kind of complicated expression for the straight line distance. So again, here is our delta sk expression, and under the radical inside each of the pairs of parentheses, we're going to divide by tk minus 1 and multiply by tk minus 1. So in effect, multiplying by 1. And then we'll factor these end tk minus 1 squareds outside the square root, and they come out as tk minus 1. And we're left with these two difference quotients inside, and then they're squared and summed. Now we're doing that because these expressions inside make us think about the derivative. There's those difference quotients. And in fact, because tk minus 1 is close to tk, we're going to apply the definition of derivative to say that this difference x of tk minus x of tk minus 1 over tk minus 1 is going to be close to the derivative x prime of tk. Again, that's if tk minus 1 is close to tk. And a similar statement holds for the difference quotient for the y. Finally, we introduced the notation we came up with earlier. tk minus 1 is delta tk. So putting all this together, we find the following, that the delta sk is approximated by, again, this straight line distance, see here, which is in turn approximated by this sum of squares of the derivatives of the x and y functions. So remember, the length of c was equal to the sum of the distances delta sk. So we now have an approximation for that sum of the delta sk's. Each delta sk is well approximated by this expression involving the square root of the sum of the squares of the x and y derivatives. So this was our goal, at least an intermediate goal. This is a Riemann sum, and it involves the tk's and the lengths delta tk, so it involves the partition of the t interval. So we can take the limit of that Riemann sum as the norm of the partition goes to 0. Remember, that means we have infinitely many partition points, and they're getting very close together. And as we've always assumed in the past, when we take that limit, the approximation becomes exact. So the length of c is given exactly by the limit of this Riemann sum, again, as the norm of the partition goes to 0. And as we've done in the past, this Riemann sum, it's easy to write it as an integral. It's the integral of the square root of x prime of t squared plus y prime of t squared under the square root dt. And since we partitioned the t interval from a to b, the a and b are the limits of the integral. And we could also choose to write this, if we wanted, as integral from a to b square root of dx dt squared plus dy dt squared dt. And in fact, this is the arc length formula we're going to be working with and applying now. You might remember in our earlier work when we found arc lengths for curves described by Cartesian equations of the form y equals f of x or x equals g of y. And we came up with this expression for the arc length element. Arc length was found by integrating this expression ds, we called it, which we found one way to write that was root dx squared plus dy squared, and then integrating that over an appropriate interval. And from this kind of generic form, we could derive the different forms that appeared in our arc length calculations. So if we have a y equals f of x description of the curve C, we would start with this ds expression, divide both things inside by dx actually dx squared, and then multiplied by dx, so we're in effect multiplying by 1. And since dx over dx is 1, and dy over dx is f prime, we came up with this expression for the arc length differential, root 1 plus f prime of x squared dx. If we had the curve described x as a function of y, so x equals g of y, a similar thing could happen here. We divide inside by dy squared under the radical, multiply by dy outside. We came up with this expression if we have the curve described as a function of y and want to do a y integral. And now we have a third part to this way of looking at ds, and again, in this last way, with parametrics, well, we could divide the inside by dt squared, multiply outside by dt, and then find this other expression for the arc length differential. And if we have parametric curves, we integrate something of this form to get arc length. We'll take a look at one example. So we're going to find the length of one arch of an epicycloid with these equations. X of theta is given by 4 cosine theta minus cosine 4 theta, and y of theta is 4 sine theta minus sine 4 theta. We'll let theta run from 0 to 2 pi. Now the epicycloid is a curve traced out by a point P as one circle rolls around the outside of a fixed circle. We discussed the equations and in fact derived the equations for the epicycloid in a previous video. If you'd like to see this video and some nice animations of the cycloid being generated, you can check out this YouTube video, and that will also be on the Canvas site for our course. Now the epicycloid described by the equations up here is for a fixed circle of radius 3, and the rolling circle, which rolls again around the exterior of the fixed circle, has radius 1. And as we saw in the previous video, the parameter theta that is convenient is take theta to be the angle formed by the x-axis and the ray from the origin through the center of the rolling circle. So we can see that illustrated over here. Here is a picture of the circle of radius 1, that's the red dotted circle, rolling around the circle of radius 3, that's the blue dotted circle. And because the little circle is 1/3 the radius of the big circle, the red circle has 1/3 the circumference of the big circle, so it takes 3 times, we generate 3 of these arcs as we go around the circle. And here's the first one. We'll find the length of that first one. Because we get these 3 arcs by symmetry, we know that that happens when we move through an angle of 2 pi over 3. And that's going to be the upper bound for our theta values. So we're going to find the length of this arc, one arc of the epicycloid, and this will happen by integrating our arc length formula with theta going from 0 to 2 pi over 3. So the length of one arc is going to be given by integrating from 0 to 2 pi over 3 ds. And because we're in parametrics, we use the parametric form for ds, the sum of the derivatives of the x and y coordinates. So x prime of theta squared plus y prime of theta squared d theta. And the rest is all just algebra and calculation. So we'll first compute these derivatives. So the x of theta was given by this. That generates the x coordinates of points on the epicycloid. We want to take that derivative and square it. And so we have this derivative here. The derivative of cosine is minus sine, which leads to the minus 4 sine term. And by the chain rule, the derivative of cosine is minus 4 sine 4 theta. And the minus here with the minus from the derivative gives us the plus sign. That's all squared, and so expanding that squared term gives us this for x prime of theta squared. Y of theta is very similar. Squaring the derivative gives us this expression. Remember, the derivative of sine is cosine. And then squaring that expression and doing the expansion leads to 16 cosine squared theta plus 16 cosine squared 4 theta minus 32 cosine theta cosine 4 theta. Now, under the radical, we want to take this x prime squared and y prime squared and add them up. And for that, we move to the next screen. Here is that sum. So the x prime squared plus y prime squared looks like this. Here is the x prime squared on top. We've written the y prime squared underneath. And that's kind of convenient because using cosine squared plus sine squared equals 1, we see these leading terms in both lines sum to 16. And again, by the same trig identity, these middle terms also sum to 16. And then in the back, we can factor out a minus 32, 4 theta from the lower equation, and the sine theta, sine 4 theta from the upper. Now we're going to simplify this a little bit. We're first going to notice that we can apply an angle subtraction formula for the cosine. So we're going to remember that cosine of any angle A minus angle B is given by cosine A, cosine B, sine A, sine B. And we see that same kind of thing up here with the A and B replaced by 4 theta and theta. So we can do a little simplification. The x prime squared plus y prime squared is this 32 from adding these two 16s. And then minus 32, and here we've applied the angle subtraction formula, taking the A to be 4 theta, the B to be theta, and that gives us cosine 3 theta. In the next step, we've multiplied both these terms by 2 and then divided by 2, and that gives us the expression 64 times 1 minus cosine 3 theta over 2. That's something we've seen earlier when working with integrals of trig functions. In particular, recall the half-angle formula we use to integrate sine squared. It says that 1 minus cosine d over 2 is the same as sine squared of the quantity d over 2. And again, this expression is duplicated right here with the d equal to 3 theta. And so we can replace the thing in parentheses by sine squared of 3 theta over 2. So you get this rather compact expression for x prime squared plus y prime squared. Now we'll put that under a square root and integrate it over the appropriate theta values. So our arc length then is given by this integral 0 to 2 pi over 3 root x prime squared plus y prime squared. We saw that this expression under the radical is equal to 64 sine squared of 3 halves theta. Of course, we have the square root, so we can take the square root of that perfect square under the radical to get 8 sine of 3 over 2 theta, and that's an easy integral. You might want to do this to be very careful by making the substitution u equal 3 halves theta, so that the d theta is replaced by 2/3 du. And that's where the 2/3 comes from here, and the integral of sine is minus cosine, which accounts for the minus sign. So we have our antiderivative. We have to put in the upper and lower limits. At 2 pi over 3, 3 halves of 2 pi over 3 gives us pi, and at the lower limit we have cosine of 0. And you can check easily that all comes out to be 33 over 2. So there is the length of one arch of the epicycloid formed when a circle of radius 1 rolls along the outside of a circle of radius 3. But a lot of important ideas come up in this video. Of course, one of the most important is how do you find arc length if curves are given parametrically? And we derive this result that if we have x given by x of t, y by y of t, and t runs from a to b, we can compute the length of the curve by doing this integral. And again, remember this thing inside here, we often will just write that as ds, the so-called arc length differential. So that ds has the form square root of dx dt all squared plus dy dt all squared, then times dt on the outside of the square root. And as we saw in the video, this can be obtained from this more general or generic form of the arc length differential. And so we see how the ds for parametrics is related through this to the ds forms that might come up when you're working with Cartesian expressions. Finally, as we saw, parametric equations often involve trigonometric functions, and the integrals that arise from working with these functions may require you have to work with trigonometric identities. So it might pay to review the angle addition formulas for the sine and the cosine. We used one for the cosine in this video. The half angle and double angle formulas also can come up. And of course, the half angle formula is very important in just doing integration in general. And you want to be sure you're up on the derivatives and antiderivatives for the trig functions. So give some practice to this. Make sure you review all these different forms of ds, and we'll see you in the next video. Bye.